All right, so so let's look at some applications. What's happening? All right, so we'll look at an electrostatic precipitator. Now, how do I get to my... Oh, there you go. All right, so do you guys know what this electrostatic precipitator is? Have you guys heard of it? Okay, so here's a factory, a smokestack, and here's the smoke coming out of the thing. So for instance, this could be a coal power plant, and all these particulate matter, if you inhale that, it causes respiratory issues. Okay, so of course you'd like to remove all these smoke particles, and the question is, how do you do that? And that's what this guy will do. Okay, so you can remove remove over 99% of the particles, and you can be like that. Okay, of course you'd like to do that. So how do we do that? So here's the idea. Okay, so the idea is the following. Okay, so let's say this is a metal plate. These are metal plates, and this is a thin wire in between the plates. Okay, so let me do a different color. Okay, and now let's say we apply, so this is a DC volt. The wire is connected to the negative terminal, and the plate is connected to the positive terminal. And let's say we apply 100,000 volts. So you have to apply a fairly high voltage. Okay. Now at these high voltages, if the wire is thin enough, what this will start doing is the wire will spit out electrons. Okay. Now let's say the smoke-filled air is sent here. Here are the smoke particles. They're fairly large. Okay. And then what will happen is, as the smoke particles are traveling, these negative charges, electrons, will stick to the smoke particles. What are these plates? They're connected to the positive terminal, so they're positively charged. What happens? These smoke particles come and stick there. All right. Okay, so what will happen is these smoke particles will stick there, and you can remove 99% of the smoke particles.
So is this in active use right now?
I'm sorry?
This is.
Oh, yeah, it is.
actively
Yeah.
being used?
Yeah.
Okay.
We had to force everybody to use it,
Right.
and we'll come to that in a second. And of course, so then you can shake these metal containers every once in a while and drop these particles off. Okay. So that's what an electrostatic precipitator is. So the wires are held at a high negative, and the plates at the positive voltage. Particles passing near the wire pick up a negative charge and stick to the positive plates. Okay. The accumulated particles are periodically shaken off. Okay. It turns out that, so if this is a coal power plant, it turns out you have to use about 1% of your electricity to clean up the air. Yeah, so that's cost money, and the companies didn't want to do that. So we had to have legislation to do that. Because, yep, anyway, people nearby would get sick. Okay. All right, so this shows you how a copier works. Okay. Now there are, do you guys know what photoconductive materials are? What would that name suggest?
Photon conductive material, like
So here's a material. In the dark, it's an insulator. And then when you shine light on it, it becomes a conductor. What do you think is happening? How does it happen?
it turns the light into electricity.
So remember, let's go back to our model. So this is an insulator where this band is empty. So you shine light and the electrons are excited from here to there, and then it becomes a conductor. Okay? So if you shine light, enough electrons are excited there, and then it becomes a conductor. Okay? So those are photoconductive materials. All right, so here's how photocopying works. So this is a metal drum, and you sprinkle the metal drum with photoconducting material, and you give it a positive charge. Okay? This all is in the dark, so the metal is a conductor. The positive charges do not run away to the metal, because that's an insulator. And here's the page you want to photocopy. You shine light on it. Wherever light fell, this material became photoconducting, and all those positive charges were neutralized. Wherever light didn't fall, it was still charged. And now you take toner and negatively charged toner and sprinkle on the drum. It sticks to only that area. Okay? And then you bring a warm piece of paper and wrap it around the drum, and that toner gets transferred. Okay? The photoconducting material is selenium. Okay? All right, so now you also know how laser printing works. Okay, instead of making an image there, for a laser printer, you just scan the drum. Whenever you want to print something, if you want to do an O there, the laser is turning off and then back on, off, and so on. So that's what your printer driver is doing. It's telling the laser when to turn on and off. Okay. All right, so these guys rely on photoconductive materials such as selenium. Okay. Did you guys understand that? Fairly neat. Okay. So again, so we are showing you applications of electric charges. Anybody deal with inkjet printers? Have you used an inkjet printer? Okay. So in an inkjet printer, so if the inkjet printer printed this page, about 100 drops per character. So this D would require 100 drops of inkjet to print that. Okay, so this needs 100 drops, and so on. Okay. Now, so let's say here's the paper. Okay. So what this cartridge does is you spit out ink drops from there. And what you do is, if you want the ink, and here's two plates, deflecting plates, which have an electric field between them. And we'll talk about this in a couple of chapters, how to create electric fields. So essentially, those are capacitor plates. You charge this plate positive, and this negative. And you can do that by connecting it to a battery. Okay? And then it'll create an electric field like that, uniform electric field like this. Okay, so that's how these plates create an electric field. And if ink drop has a negative charge, it gets deflected like so. If an ink drop has no charge, it goes straight. What do you want? What do you do if you have to deflect it more? You give it more charge. Okay? Okay. So, input signals from a computer controls the charge given to each drop, and thus how much the drop is deflected from the plates. So, this is the right edge of the plate, and so the right edge of the paper, that's what those are being printed. And the left edge, this stuff is getting the most charge, and those drops get deflected. So here the printer driver is telling the laser when to turn on and off. Here the printer driver is telling how much charge to give to each drop. Okay. All right. So that was that. All right. Now we'll talk about field forces. Okay. The question is the following. Okay. So here's this proton and here's this proton, or positively charged particle. There's this positively charged. What do they do to each other? I'm sorry?
They reflect each other, right?
They repel each other.
Yeah.
Okay. What if this guy was in Palm Coast? And this guy was in Daytona? Will it still repel it?
Well, it has infinite range.
All right, very good. In New York, it'll repel it. How does it repel it? Right? So people thought about that. So that was the question. And here's the answer to that. So the story is, okay, so if you have a positive charge, what this positive charge does is it creates an electric field all around it. How far? All the way to infinity. And presumably this electric field gets weaker the further you are. Okay? And if you have another charge here, that charge is just feeling the electric field locally. It doesn't know what created it. All it's doing is it's responding to the local conditions. Okay? So if this was in Palm Coast, the electric field obviously is stronger and it feels a stronger force. And you learn in a second the force is equal to this charge times the strength of the electric field where the charge is. Okay? So if the charge is positive, the force will be in the same direction as the electric field. Okay? And if the charge is negative, it'll feel a force in the opposite direction. Okay? So did you guys understand that? So forces at a distance are really mediated by an electric field. Okay, so that's the story. So now we'll learn about electric fields. Okay, so we'll see what kind of electric fields do charges produce. Okay, so for instance, if you have a positive charge, you will soon learn it produces radially outward electric fields. Okay? And so these are vector fields. Okay. And if you have a negative charge, it produces an electric field pointing towards the negative charge. Okay. What do you think happens if you have two charges? If you're rich and you have two charges? So field lines will go out radially and come in, okay? Like that. So this is how the field lines will look like. Okay, so there's the field lines of a dipole. This is called a dipole. See, field lines start at a positive charge and end up on the negative charge. So we will plot these lines in lab. Okay. All right, so electric and gravitational forces are field forces. Particles interact with other distant particles by setting up fields all around themselves. Okay, these fields in turn affect other particles. So if you have a charged particle, it'll create an electric field all around it. And if you place another particle in the field, it'll feel that field. If this particle didn't exist, that field wouldn't exist, and this particle would be unaffected. Okay? So these electric fields are created by, it could be created by this particle and many other particles. Okay? And you place another particle there, a test charge there, and it'll feel whatever field is there. Okay? And react to that field. All right, so two equal and opposite charges separated by each other, they're called a dipole. So they're called a dipole. Okay, and these things are important, and we'll study them. Okay, so here's how the field looks like. So electric field lines begin on a positive charge and end on a negative charge. Okay? Electric fields in general are functions of time and spatial coordinate. Okay, so you see the electric field strength is changing at different locations. And if you move this charge, if you jiggle this charge, of course, the electric field will change with time. Okay? But if the charges are stationary, then it won't change with time. But okay. So here's a cross-sectional view. There is a dipole, equal and opposite charges. Okay, and this is how the field line looks like, and this is what you'll plot in lab. Okay. Now here's the deal. Okay, so let's look at an atom. We've been looking at the atom quite a bit this class. All right, so there's the nucleus. It has a bunch of positive charges, protons, and a bunch of neutrons. Okay, and here are the electrons. Okay, how many protons? 1, 2, 3, 4, 5. So now for every atom, there's about 100 different kinds of atoms, 92 really naturally occurring. For every atom, the center of positive charge is there, and the center of these negative charges is right on top of it. Okay? So for every atom, if you're far away, this appears as a neutral particle. Okay? Again, the center of positive charge and the center of negative charge is right on top of each other. Did you guys understand that? So the dipole moment of every atom is 0. Okay. All right. So this here's a dipole. Okay. There the positive and a negative charge are separated by each other. Okay, and this is how the electric field looks like. So, okay, what this is showing you is the electric fields created by some charge distribution like that. Okay. The strength of the electric field at this location is conveyed by drawing a larger number of line density. If you want to indicate a stronger field, you just draw more lines. If you want to indicate a weaker field, there are less lines per unit area. Okay, so the density of lines conveys the strength of the field. All right, so let's say you have a electric field like that. So these are electric field lines. What that means is at a given location, the field is tangent to that line. Okay. Okay, so at this location, the field is like that. At this location, the field is like that, and so on. Okay. The electric field at a given location is tangent to the line. Now, if you have a field line at that point, if you place a positive charge, the force on the positive charge is in the same direction as the field line. If you place a negative charge, it's in the opposite direction. Okay? So, positive charges are pushed in the direction of the electric field, negative charges move in the direction opposite to the electric field. Okay? And that makes sense. So you guys remember, here's a positive charge creating an electric field like that. If you put a positive charge, it gets repelled. If you put a negative charge here, it gets attracted. So negative charges move in opposite direction to the electric field, and positive charges move in the same direction as the electric field. Okay? So the force on the charge is Q times the electric field. So this actually is a definition for the electric field. The electric field is defined as the force per unit charge. Okay, how strong is the electric field there? Well, measure the force on this particle, and the force divided by this charge gives you the electric field. Okay. Right, so the units of the electric field are, this is measured in newtons, and this charge is measured in coulombs, in honor of Mr. Coulomb. So electric fields have units of Newton per Coulomb. Okay. Okay, so here's a positive charge, and it's creating electric fields like that. Here's a negative charge, and it's creating electric fields like this. Okay. Now, if you ask the question, how strong is the electric field at this point? You know the direction. The strength of the electric field is given by, this is the Coulomb's constant. Q is the charge creating the electric field, divided by R squared. Okay. So the electric field falls off as 1 over R squared. Okay. And if you check your notes, this is just like the gravitational field, mass divided by R squared. Okay. Acceleration due to gravity falls off as 1 over R squared, just like that. So the formula are almost identical. R hat is a unit radial vector. Okay. So the electric field is pointing radially outwards. Now, if the charge happens to be negative, this will be negative, and the field will be pointing in the opposite direction. Okay, R hat is a vector pointing in that direction, is a unit vector pointing in that direction. All right, so the strength of the electric field, just the magnitude, is given by KQ over R squared. Okay, so that's an important formula to remember. Now, it turns out that whenever you're dealing with charges, you'll have many charges, and then you'll need to know the electric field everywhere. So to calculate the electric field at this point, it's the electric field due to this guy, plus the electric field due to this guy, plus the electric field due to this guy, plus the electric field due to all these guys. So you have to add all these vectors up. And then you're not happy with just the electric field at this point. You need an electric field at this point, So if you had a bunch of charges in this room and you wanted the electric field everywhere, you'd be here forever. Okay? So in the next chapter, we'll learn about Gauss's law that will help us calculate electric fields in symmetric situation. Okay? So for instance, it'll help us calculate the electric field. Let's say if you smear the right wall evenly with positive charges and the left wall evenly with negative charges, it'll let you Gauss's law will help you calculate the electric field without having to add up all these electric fields. Okay? Because you will be interested in the electric field in a region. Okay? So you will need to know this. What is this? You need to know the electric field at all locations. Okay. All right. So we mentioned an electric dipole. What is an electric dipole? It's two equal and opposite charges separated by a distance. What is the dipole moment of atoms? I'm sorry?
It's zero.
Right. So the center of positive charge is right on top of the center of negative charge for all atoms. So the dipole moment of all atoms are zero, so why are we talking about this stuff? Why bother talking about it? All right, so what is this? That's Mickey Mouse. All right, this is H2O. This is the oxygen atom. There is the hydrogen atom. Now the oxygen atom happens to be greedy for electrons. The hydrogen atom is happy to give out its electron. Remember, the hydrogen atom is on the left column, oxygen is to the right. Oxygen wants electrons. Okay, so the electrons from there migrate closer to the oxygen atom. Okay, so it turns out that even though the oxygen atom by itself would have no dipole moment, but because it grabs the electrons from there, now the center of the negative charge for the whole molecule is there, and the center of the positive charge for the whole molecule is there. So a water molecule has a dipole moment. Yeah. And this will be extremely important. Did you guys understand that? So here's a molecule. So there are molecules that can have dipole moments. Okay, the dipole moment is denoted by P, and it's the charge times the distance between them. Okay, so the further apart they are, the greater the dipole moment. The greater the charge, the greater the dipole moment. Okay, now it's very hard to have a large dipole moment, I guess. But anyway, so why is it hard to have a dipole moment? So what do these guys want to do? They want to attract each other. So it's like having a stretched spring. Okay? So there's energy stored in that. Okay? So anyway, so here is a molecule that has a dipole moment to it. Okay? All right, now what can you do with this? So here's an absolutely amazing fact. See, life would not be possible without dipole moments. Okay, so what we'll do is, we'll build a molecule like this. This molecule has a polar head and a non-polar tail. Okay, this tail doesn't care about water, but this tail, because it has a polar head, it wants to attract water molecules. Okay, so now we'll do the following experiment. So here's a jar of water. Okay, and what we'll do is, we'll take those molecules that we made and throw a bunch of them in the water. What do you think will happen? Okay, so here's what happens. So these are polar, right? And water molecules are these Mickey Mouse molecules with negative there and positive there. Okay, so all these guys, okay, well, actually, let me do yeah. So these guys will attract to water molecules like that. This is the lowest energy configuration. Okay, so when you have a bunch of these guys, what happens is the following. The heads want to attract water molecules. The tails don't care. So you throw a bunch of these guys in the jar, in a beaker of water, they all arrange like this. They'll arrange like a balloon. This is a cell. This is so this is a cell. This is the inside of a cell. This is the outside of a cell. And now you can create life in here. So that wouldn't be possible without dipole moments. Did you guys understand that? Okay, so this is a low energy configuration. Okay, you throw a bunch of bilipid, phospholipid molecules. These are phospholipid molecules into a beaker of water, and you'll have a cell automatically form. Okay? Pretty amazing. So that's what this is. Okay, so the polar heads want to face the water molecules, and these guys. They're called hydrophobic, but they're neutral to water because they're not, they don't have dipole moments. Okay. Now, so here's a single charge. The electric field of this charge, its strength falls off as Q over R squared. Okay. So what we want to show you is the following now. So now let's say we have considered the next complex stuff. Here's a dipole moment. Let's look at the field at this point for the dipole moment. The positive charge creates a field in this direction. The negative charge creates a field in this direction. Since the negative charge is further, this field is weaker than that field. And the net field there is the sum of these two fields, which is in that direction. Okay? And the net field in this direction turns out to be proportional is z cubed. It's falling off as z is this distance. So the strength of the net field at this point is falling off as 1 over z cubed, faster than that. All right? So the field from a single charge, point charge, falls off as 1 over r squared. The field of a dipole falls off as 1 over r cubed. Okay? That's what that is showing you. Okay. I'm not going to go through the details of this, but that's what you want to remember. Okay, so again, what we are saying is the field falls off as 1 over r squared. R is this distance. And from a dipole, the field falls off as 1 over r cubed. Okay. So the field falls off faster. Okay, so the further out you are from dipole, the more neutral it appears, and that makes sense. So if you're looking at a water molecule from New York, this water molecule here in Palm Coast will appear neutral. Okay. All right. Now we want to deal with the following. Okay, so you know how to calculate the electric field from a point charge, which is kq by r squared. Okay. And you guys are all calculus experts, Calc 3 experts. So now what we're going to do is we're going to throw, this is too easy, so we're going to throw a more complex problem at you. Okay, what we're going to do is we're going to throw a thundercloud at you. And the thundercloud has a bunch of charges, let's say uniformly distributed. And what you want to do is calculate the electric field on top of your house due to this thundercloud. Well, you know this formula and you know calculus. So what do? You take this thundercloud, break it up into little chunks. The charge of this, you know how to calculate the electric field due to this guy. Okay? The electric field due to this guy, so let's say the charge of this is dq, which is that. K dq divided by r squared, there, that distance. And the electric field is in the direction of r hat. And then you would sum over all the pieces, and that's what the integral is. So this would be a 3D integral. Okay. Now, in most cases, this integral is impossible to do. Okay. But here's an expression in principle. Okay. So impossible to do in most real life cases, most cases. Okay. So there will be some special cases where you can actually do that integral. Okay. But that's how you would calculate the electric field at any point due to a charge distribution. Okay. And we'll show you some examples of how to do this integral. Okay. Did you guys understand this? So this is just a generalization of Coulomb's law. Okay. So here's the Coulomb's law for this little piece. And what is that integral sign doing? It's just summing over all the pieces. Okay. You guys understand? All right. All right, so before we do that, what we'll do is, there'll be situations when you'll be dealing with a charge distribution, so you'll need the density, volume density of charge. Okay, so that's what this is. So if that was the total charge of the thundercloud, total charge, and assuming uniform distribution, total charge divided by volume, that gives you the charge, volume charge density, denoted by rho. Okay. Oftentimes you'll smear a wall evenly with charges, okay? And then you need a surface charge density. So when you're dealing with capacitors, you'll do that. So for instance, you can spray that wall evenly with charges. So the total charge divided by the area gives you the surface charge density. Okay? And then there will be times when you will deal with linear charge density. Okay, you'll take a wire and smear it evenly with charge. Okay, okay, so this is linear charge density denoted by lambda. Total charge divided by the length of the wire. All right, so again, ultimately when you're calculating electric fields, you'll be using that expression. And like I said, this integral is very hard to do except in very special cases. Okay, so I'll show you the special cases. So here's, let's say you take a ring and smear this evenly with charge. And now what you want to use is the linear charge density. What we're going to do is, so now you want to calculate the electric field due to this guy. So essentially this is the integral you want to do. K dq divided by r square r hat. You're going to apply this, and dq will be the charge of little pieces like that. Okay. Now this integral is impossible to do if you wanted to find the electric field there. Okay. You wanted to find the electric field there, you couldn't do that integral. You can do this integral if you wanted to find the electric field at axial points, only along on the axis. Okay. And this integral is done here for you. And along axial points, there's the electric field. Okay. Along axial points. So that is the total charge on the ring. A is the radius of the ring, and x is that distance. Okay. Again, you don't have to remember any of this stuff. All I'm telling you is, what I want you to remember is that this integral is very hard to do in most cases. For this special case of these points, you can do that integral. Okay. Can you find the electric field at this point? No, you couldn't do that integral. Okay. So for these points you couldn't. You can do it for these points. Okay. And that's the expression. Along the axis. Okay. Here's another charge distribution at disks evenly smeared with charges. Again, you can do that integral for these points. Okay. So that is the integral you're doing. Okay. K dq by r square r Okay. And what you're doing is you're breaking this disk into little rings, and you have the expression for the rings from here, and you're using that. Okay. How about here? Can I find the electric field at this point? No, I couldn't find.
It's not on the disk.
I'm sorry?
Is it the point not on the disk?
No, the point has to be on the axis of the disk. You can only find electric fields at these points. Okay, at any other point you cannot find. It would be almost impossible to do that integral. Okay.
Where does that two come from in front of the pi r? In the formula?
Oh, when you're doing the integral, it comes from the circumference of the ring, 2 pi r. Mhm. Okay. All right, so here's another. So again, notice that I'm not doing the integral. I'm just telling you it's possible to do those integrals, and those integrals have been done. Okay, so here's a surface and you smear this evenly with charge. Okay, and let's calculate the electric field. So you can take a plastic sheet and smear it with charge, and you want to calculate the electric field on either side. Okay, and this field is evaluated, and there's the answer. What is sigma? Sigma is the surface charge density, meaning charge per unit area. Okay, how much charge there is per meter square of this surface. Okay, now this expression is valid if this is an infinite sheet, infinite flat sheet. Okay, so this sheet has to be flat and infinite. Then the electric field on this side is sigma, the surface charge density, divided by 2 epsilon naught. Epsilon naught is a constant. It's called the permittivity of free space, and it's related to the Coulomb's constant, like so. Okay. And epsilon naught is called the permittivity of free space. All right. Now, there's something very strange about this expression. Let's see if you guys can notice that. What's strange about this expression? So this is giving you an electric field at that point. So this is an infinite flat sheet, evenly smeared with charge, and that's the surface charge density. And the electric field at that point is given by this expression. And I'm telling you that there's something very strange about this expression. Can you tell me what's strange about it?
Isn't the area just infinity? So the top expression.
Where is this? Where is the location of this charge?
Everywhere.
Right? There's no distance information. This charge could be that wall, and it could be in this room. It could be, this point could be in New York. It could be in the next galaxy. The electric field is the same on this half of the universe, and it's the same in this half of the universe. All right? So, okay, the electric fields, if you have an infinite sheet, then the electric field is constant on either hand. Okay? All right. What is this? Lightning. Do you know how that happens?
I don't know the science behind it, no. I just like size like.
I'm sorry?
Isn't there a bunch of electrons in the atmosphere? There's a bunch on below.
Uh, there's air in this room, water, air, nitrogen, and oxygen. They're neutral. So right now, this won't conduct electricity. But this is electricity being conducted from ground to the cloud. So how come this air, which is neutral, became conducting? That's the question. Did you guys understand that? Okay. So here's how you do lightning. Okay, so what we'll do is, oh wow, I gotta finish this very soon. But this is important, you gotta know this. So let's say here's a thundercloud that's positively charged, and we'll get to that later. How did it become charged? Okay. And it attracts negative charge in the ground. Okay, so now we want to discharge this cloud, except that we have a whole bunch of neutral atoms, and they won't conduct electricity. Yep. What this does is it creates an electric field. It creates an electric field like that. But if you have a bunch of neutral particles, these guys don't care about the electric field. Yep. But here's the deal. So every once in a while, you'll have a stray electron. And what does the electric field do? It makes the electron accelerate in this direction. Okay. Now the electron, of course, collides with these neutral atoms. With these neutral atoms. Okay. So the electron will travel a certain distance and then collide with them. Okay. Now, if the electric field is strong enough, where the acceleration is large, okay, so large acceleration, electric field strong enough, where the acceleration is large, this will accelerate, and before it collides, it gains enough speed where it starts knocking off electrons from them. Okay. But for that to happen, you need a strong electric field, a large enough acceleration so that when it's before it collides with these atoms, it gains enough speed where it starts knocking off electrons. Okay. So now, if the electric field is strong enough, it knocks off a bunch of electrons from the air molecules, and now you have a conducting path, and lightning will strike. Okay. So the question is, how strong an electric field do you need? Okay. So it turns out that if the electric field is, for air, it's 3 million volts per meter. Okay, that's a different unit for electric fields. But if the electric field strength, if this field strength is greater than 3 million volts per meter, then the air will break down, meaning the neutral air will become conducting, and you can have lightning strike. Okay. So what this also tells you is, every time you see a spark in air, the electric field at that location was greater than 3 million volts per meter. Okay. So for instance, in your cars, in your cylinder, how's the air-fuel mixture burned? Through a spark plug, which creates a spark. So in the spark gap, the electric field was greater than that. So if the spark gap is I don't know if you guys know, that's how the spark gap looks like. If the spark gap is 1 millimeter, then to have that electric field, you have to have 3,000 volts between them, okay, to create spark. Okay. All right, so this is an important number. So spark in air, it has to be greater than 3 million volts per meter. Okay. All right, I'm going to quickly finish this. So here's we'll learn about capacitors. Here's a charge capacitor, and it creates an electric field like that. And if you put a positive charge like there, it will move toward the negative plate. Okay, so here's those plates. If you shoot an electron between them, the electron will get attracted toward the positive plate, and it gets deflected like that. Okay, so back in the old days, CRT tubes had things like this. So you would have an electron beam, and here were two deflecting plates, and here was the screen. When the electron hits a phosphorescent dot, that would emit light. So let's say if this was the screen, so the electron beam is hitting those dots like that. Okay, and it's drawing over 30, it's scanning the screen over 30 times a second. Okay, so to get a continuous motion. So here is the water molecule, famous water molecule with a dipole moment. And here's something very important that you learn. Okay, so here is an electric field, there is the dipole moment. Okay, so I'm going to draw a simplified picture. So here's an electric field, and the dipole is, here's the dipole. The water molecule, there's the center of positive charge, there is the center of the negative charge. Okay, so, and again, just so you have a picture, so here's the water molecule like that in this location. So there's the dipole moment. Okay, what does the electric field do? The electric field applies a force. The positive charge wants to move in this direction, and the negative charge wants to move in this direction. Okay, so what the electric field has done is it's grabbed the water molecule and it's turning the water molecule. It wants to turn the water molecule such that the water molecule lines up like this. Okay, so an electric field will grab a molecule with a dipole moment and turn it like that. So it will turn it like that. Did you guys understand that? Okay, so here's a very important application. So once it's turned it like that, what you do is now switch the electric field. Now what happens? Now the electric field wants to turn it the other way. Switch it back. It turns it this way. So you can use an electric field to grab a water molecule and jiggle it like back and forth like this. That's what a microwave does. It switches the electric field back and forth 5 billion times a second. 5 gigahertz. So that's how it heats a water molecule. That's how it heats your food. All foods have water in it. So it'll heat the water molecule by jiggling it back and forth, and then the water shares its heat with the surrounding food, with all the food. Did you guys understand that? So dipole moments are very useful. Okay. So, all right. So dipole moments also have potential energy. So when an object falls from a higher to a lower location, the potential energy is being converted to kinetic energy. So just like that, as a dipole rotates, its potential energy is being converted to kinetic energy. So the potential energy denoted by U is negative of P dot E. Okay, so there's the dipole moment, there's E. Okay, so if the electric field is like that, the dipole has maximum potential energy in this configuration, and it has minimum potential energy in this configuration. Okay, so when P dot E is positive, the potential energy is minimum. When P dot E is negative, potential energy is maximum. When this is negative, 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 will give you positive. Okay. All right, so when you have dipoles, you can do a whole bunch of stuff. Okay, so now you know how microwaves work. Okay. All right, that finishes this chapter.